In this session of work, energy and power, we are going to apply the concept of work kinetic energy theorem. Now, first of all, we are going to revise the concept of work kinetic energy theorem, and work kinetic energy theorem will be given by work done equal to final kinetic energy minus initial kinetic energy. This one is the work kinetic energy theorem, right? And that we have discussed in the previous sessions. Now we are going to revise the concept of work done by the spring force, and this concept was discussed in the previous session. The work done by the spring force, if this spring is extended from the position x1 to position x2, will be given by minus half k x2 square minus x1 square, right? In this session we are going to discuss a very important problem, and the problem is that this one is the block which is moving with the speed u and collides with this spring. The spring constant of the spring is k, right? And the surface having some friction, and the coefficient of kinetic friction is given by mu, right? Now the block is compressing this spring, and due to the compression of the spring, the speed of the block will decrease, and we have to find the maximum compression in the spring, right? That means you can see in this figure, the block is compressing this spring with speed u, and at this moment the spring will have maximum compression and the speed of the block will become 0. This one is a very important application of work kinetic energy theorem. This block has the mass m, and this block is moving with the speed u on a frictional surface. This frictional surface has the coefficient of kinetic friction equals to mu, right? The block is colliding with the spring of spring constant k with the speed u. We have to find the maximum compression in the spring produced by the block, right? As we know that the speed of the block will decrease, and at the moment of maximum compression of the spring, the speed of the block will become 0. Now you can see in this figure, the spring is compressed by an amount x, and you can say that this x is the maximum compression produced in the spring by the block, and at this moment the speed of the block is 0, right? We have to find this x. For this we have to apply the work kinetic energy theorem in this problem to get the value of x, and according to the work kinetic energy theorem, work done equal to change in kinetic energy. That means total work done performed by different forces acting on the block, that will be equal to change in kinetic energy. Initial kinetic energy of the block is half mu square, and the final kinetic energy of the block equals to 0. Hence, by applying the work kinetic energy, we can get the value of x. Now, according to the work kinetic energy theorem, that work done will be equal to 0 minus half mu square, right? This one is the final kinetic energy, or this one is the initial kinetic energy. Now our purpose to find the total work done by the different forces acting on the block. Now for this we have to draw the free body diagram, and the free body diagram of this block will be given by one force is the spring force kx, another one is the normal reaction which is acted by the surface on the block vertical upward, next one is the force mg, and the fourth one is the force of friction, and this frictional force will have the kinetic frictional force, and this is given by mu into n. This mu is called the coefficient of kinetic friction, right? The value of normal reaction will be simply equal to mg, that you can see, hence the frictional force will be equal to mu mg. Now we have to find the work done by all these forces. We are going to find the work done by the normal reaction. Work done by the normal reaction will be 0, because the normal reaction is vertical upward and the displacement of the block is along the horizontal direction, and the angle between the normal reaction and the displacement of the block is 90 degree, hence the work done by the normal reaction will come out 0. In the similar way, the work done by the weight mg will come out 0, because weight mg is acting vertical downward and the displacement is along the horizontal direction. The angle between the force and the displacement is 90 degree, hence the work done by the weight mg will come out 0. Now the next one, work done by the spring force. Work done by the spring force will be given by minus half kx square. Now we are going to find the work done by the frictional force. Work done by the frictional force, right? The frictional force is acting towards left and the displacement of the block is towards right. Hence the angle between the frictional force and the displacement of the block is 180 degree. Hence the work done by the frictional force will be given by mu into n, this one is the frictional force, into displacement of the block x into cos of 180 degree, right? As we know that the value of the normal reaction is mg, cos 180 degree minus 1, hence this work will come out minus mu mgx. Hence the W will be equal to the algebraic sum of these two work. Now the equation will become, right? The equation will become minus half kx square minus mu mgx, that will be equal to minus half mu square. Now we have to solve this equation. As you can see that the equation is quadratic one, right? One is the quadratic equation. After solving this equation, this quadratic equation will have the two values of x, and out of these two values only one value of x will be accepted. Now you can see that one value of x is negative and other value of x is positive. Only the positive value of x will be considered. Hence this one is the maximum compression produced in the spring by the block. This one is the maximum compression produced in the spring by the block.